All right, so our last speaker this session is Anton Arnold from TU Vienna, and he'll speak on the short and long-time behavior in evolution equations and the role of the hypocoercivity index.
So thank you very much for the introduction, and most of all, thanks to the organizers for the kind invitation. So let me mention that what I'm presenting is joint work with my two postdocs, here, Franz Achleitner and Eduard Nigsch, as well as with Eric and Volker Mehrmann, who is in Berlin. So just to give you the framework of what I'm going to talk about, I'm interested here in linear evolution equations with a generator L that is constant in time. I assume that the system is semi-dissipative in the sense that the Hermitian part of the operator matrix is positive semi-definite, and I assume that this operator L has a unique steady state. So this operator L is called hypocoercive if there are positive constants C and a coefficient mu, such that you uniformly have this exponential decay towards the unique steady state f infinity. And as I will partly also speak about ODEs, so in that setting, hypocoercive is nothing but positive stable, meaning that all the eigenvalues are in the right half plane. So just to give you more intuition of what will appear, the key notion that I will introduce is the hypocoercivity index, which is a measure of how hypocoercive or how degenerate my generator is. So let's first look at the left picture. What I show you here as a function of time is the norm of some sample trajectories of an ODE. So you see a decay in a wiggly fashion. And that's a typical manifestation of what happens in hypocoercive systems. And the red curve here is the envelope of that. So that's the norm of the matrix exponential. And the green curve on top of that is then the exponential estimate that I had on my previous slide. On the right-hand side, you see a numerical simulation taken from this paper by Hilbert, Moore, and Paresky. So let's just look at this dashed curve. What they show there is the relative entropy, again, as a function of time with respect to the global Maxwellian. And again, you see this wiggly decay, which most likely is also a manifestation of the same mechanism. So the goal of this talk will be that I want to connect the hypocoercivity to both the short and large time behavior or decay in such systems. So here's the outline of the talk. I will start with hypocoercive ODEs, say as a warm-up, then discuss Fokker-Planck equations, and in the end, Hilbert space evolution equations. So let me start super simple. I start with non-symmetric ODEs, so this matrix C should be non-symmetric, and I say that this matrix is coercive if the Hermitian part of the matrix is bounded below by a positive constant. So let me just start with this very simple 2x2 example, which is not coercive, because you have this 0 on the diagonal here. The eigenvalues have a real part which is 1/2, so the decay rate of all solutions to this equation is 1/2. But since it's not coercive, you will not be able to extract the decay of any trajectory by the simple energy method. And by this I mean, if you multiply your ODE from the left just with x, you will not see this decay with a rate 1/2. However, if you introduce this weighted or modified norm where matrix P is stuck in between these two x, and in this example, a convenient matrix P has these entries 2, -1, -1, 2. Then here as a plot, as a function of time, you see this very nice red curve where you have this nice exponential convex decay, while the blue curve corresponding to the Euclidean norm decays in this wiggly way. So one of the main themes of the analysis of the large time behavior of hypocoercive PDEs is the construction exactly of such strictly decaying Lyapunov functionals. In my talk today, this will not be the theme. So I will stick to the given norm, and I want to discuss this wiggly behavior. So as I mentioned, hypocoercivity for such an ODE just means that all the eigenvalues should be in the right half plane, and I will discuss semi-dissipative systems. So I will split this matrix C into its Hermitian and skew-symmetric part, assuming that the Hermitian part is positive semi-definite. And then the condition for hypocoercivity will be that no subspace of the kernel of the Hermitian part is invariant under the skew-Hermitian part. The key notion I want to introduce in this talk is the hypocoercivity index, which was formulated in this joint paper with Franz and Eric. So again, for a semi-dissipative system, I say that the hypocoercivity index of this matrix is the smallest integer such that the sum of these matrix products is positive definite. So before we discuss this sum, let me go to the first remark. As I defined, the matrix C is coercive if its Hermitian part is positive definite. So in this case, there's no need to add anything to the lowest order to j equals 0 term, because that Hermitian part is already positive definite. In this case, the index is 0. If this is not the case, you just go on and sandwich the Hermitian part between powers of the skew-Hermitian part, and go on until eventually it becomes positive definite. If this happens with a finite number of times, then this matrix is hypocoercive. I should say, in the finite case, or in finite dimensions, infinite index cannot appear, but in the Hilbert space case, this indeed can happen. For algebraic reasons, there's a lower and upper bound for this index in terms of the rank of the Hermitian part of your matrix, and the maximum index that you can see is space dimension -1. So just intuitively, this index gives you a characterization how complicated the intertwinement between the Hermitian and the skew-Hermitian part of the matrix is. So let me illustrate that on one example. Let's take as a Hermitian part of a 4x4 system this diagonal matrix with 2 zeros and 2 ones as the entries. So if your evolution just has this symmetric part, the first two directions, of course, don't decay. The third and the fourth, they will decay. So now let's just add this skew-Hermitian matrix, and let me look at this 2 by 2 submatrix in the center, which represents a rotation. So this matrix mixes or connects the second with the third direction. Therefore, eventually also, initial conditions in the second direction will decay eventually because of this coupling. Next, let's look at the 4 corners of this matrix, which is the same rotation as before, and it connects the first original non-decaying direction to a decaying direction, the fourth direction. So each original non-decaying direction is connected by a single rotation to a decaying direction. So therefore the index is 1. By contrast, let's look at this skew-Hermitian matrix. Let's look at the upper left rotation matrix here. It connects the first to the second direction, which again does not decay. Then let's look at the central 2 by 2 matrix. This rotation connects the second to the third direction, so eventually all initial conditions will decay. But you have a chain of rotations, therefore the index in this example is 2. This hypocoercivity index gives us a very clear connection of how the propagator norm, that's the spectral norm of the matrix exponential, decays for short time. So originally at t equals 0, this norm is of course 1. The system is semi-dissipative, so it will become eventually smaller than 1. And I'm interested in what is the leading term here in a Taylor expansion, what is the dominant exponent in this first term. And the theorem tells us this exponent, the leading exponent, is twice the hypocoercivity index plus 1, plus higher order terms. Plus, in the theorem, we also have an explicit form of this multiplicative constant C in terms of the Hermitian and skew-Hermitian part of the matrix. I don't give the formula here because the formula per se is not very instructive. The proof of this purely ODE theorem is surprisingly technical. We needed to separately derive an upper and a lower bound. And one of the reasons why this proof is so technical is when you want to extract or obtain the sharp constant C, you notice that the sharp constant is not realized by any single trajectory, only as an envelope. As an envelope, if you choose very well a family of initial conditions, then you're able to obtain this optimal constant. And what we also used here is that this propagator norm is analytic on a small neighborhood of t equals 0 in the matrix case. So let's look at this example that I've discussed before. It has index 1. Here what we see in a semi-logarithmic plot for large time is these straight lines, which reflects that all solutions, all trajectories decay exponentially. So I've included here a small epsilon in front of the skew-Hermitian contribution. As an illustration of the theorem that I had just before, I zoom in here to the situation close to t equals 0 in a double logarithmic plot. So there we see these straight lines. Now in a double logarithmic plot, they correspond to a purely polynomial behavior. So in these hypocoercive systems, for short time you have a polynomial decay, and only then the well-known exponential decay. And here we see we have this t to the power 3, which corresponds to the hypocoercivity index equal to 1. So let me continue on the phenomenological level a little bit with one more example. Let's look at, oops, this was the wrong button. Let me look at this example here. So the diagonal, the symmetric part, just has one non-zero entry, and then I have this skew-Hermitian matrix with the 1s and -1. In this situation, I have the maximum hypocoercivity index, and I'm comparing here the situation with an index 2 and an index 6. So the color code is as follows. The blue curve is the propagator norm of the matrix exponential. The red curve is the asymptotic behavior close to t equals 0 from the theorem. And the green curve is the uniform exponential estimate that I put on top of that. So what we see is, particularly for large indices, that initially you have almost a plateau where the propagator norm does not decay almost at all. You stick to 1. And then very quickly you switch from there, from this polynomial behavior, to the well-known exponential decay. So let me now come to Fokker-Planck equations. And for the Fokker-Planck equations, I want to compare to you two different behaviors for the short and the large time. So let me start here with Fokker-Planck equations that have a linear drift. So this drift matrix C is constant, and D is a degenerate diffusion matrix, also constant. First, I remark that this Fokker-Planck equation can be normalized just by rotating and squeezing the coordinate system, such that the diffusion matrix can always be equal to the Hermitian part of the drift matrix. Under this normalization, the steady state will then just be the standard Gaussian. And I assume that on the following slides. Again, as for the ODEs, the condition for hypocoercivity is that no subspace of the kernel of your degenerate diffusion matrix is invariant under the transpose of the drift matrix. So I assume that my Fokker-Planck equation now is hypocoercive with some index. And this result, jointly with Christian Schmeisser and my former student Pierre Signorello, tells us what the key result is here, the red part of the theorem. Here on the left, I have the propagator norm of the PDE, of the Fokker-Planck equation. And the norm is taken in the sense of bounded operators on this weighted L2 space. Since the convergence of the Fokker-Planck equation is to a steady state, to the Gaussian, I take out here the projection onto the steady state. And this PDE propagator norm is exactly the same as the ODE propagator norm for all time. And here the propagator norm for the ODE is derived from the drift ODE, where you only keep the matrix C. And for that ODE, we had this theorem before that for a short time you can characterize that in the Taylor expansion in this way. So what this tells us, as they remark on the last line, if you have a large hypocoercivity index in your Fokker-Planck equation, this will delay the onset of your exponential decay. So in this sense, a large index is bad for the decay if this is what you want to see. Now, a second feature with an opposing effect. It is well known that in Fokker-Planck equations, if you add a non-symmetric drift, think of a rotation, this can speed up the convergence to the steady state. Compared to the setting where you only have a symmetric evolution. So assume in this question that the steady state is given. Think of it as non-isotropic to make the question interesting. The question I want to address is which Fokker-Planck equation, meaning which drift matrix, which diffusion matrix gives you the fastest decay in this exponential sense to the fixed given steady state. In the following sense, you first want to maximize the exponential rate, and then secondly, afterwards, you want to minimize the multiplicative constant, larger or equal to 1. To make the problem well posed, you have to give a limit to the trace of the diffusion matrix, so let's fix that. So there's previous results on these questions. So Guyen and Montmarché, they already extracted the information that the best possible exponential decay rate is the largest eigenvalue of the matrix k minus 1, which appears here in your fixed Gaussian. And they also found out that the best diffusion matrix, which can be constructed, will be very singular, and the range of this optimal diffusion matrix is in the eigenspace of this largest eigenvalue. So together with Signorello, we built on this result and also added that for any multiplicative constant arbitrarily close to 1, you can construct a drift matrix such that this decay estimate holds with the optimal rate and with a C arbitrarily close to 1. So let me come back to the special situation where this largest eigenvalue from k minus 1 is a simple eigenvalue. In this case, the rank of your optimal diffusion matrix is just 1, which means that in this case, the hypocoercivity index of your Fokker-Planck equation will be maximal, space dimension minus 1. So in this case, where the largest eigenvalue is simple, a high hypocoercivity index is good in the sense that it provides you the largest or the fastest decay, in contrast to the situation for the short-time behavior where it was bad. So after all this algebraic preparation, let me come to more interesting evolution equations in Hilbert spaces. So here now C for me is a bounded operator because I don't want to deal here with domain issues. Again, the setting will be semi-dissipative in many physical systems this is the original setting anyhow, and for convenience of the presentation here, I assume that the kernel of this operator is trivial, so I assume that the conserved quantities have already been taken out of the space. So again, I split the operator in its symmetric and skew-symmetric part. Hypocoercivity is defined as before, as having exponential decay. In the terminology of semigroups, this would say the generator generates a uniformly exponentially stable semigroup. And the key notion is again the hypocoercivity index. So you again have the sum now of these operator products being now uniformly bounded away to zero. So in the infinite dimensional case, you need this uniform bound with the kappa times the identity operator. This is important here. So in this setting, together with Achleitner, Mehrmann, and Nigsch, we have the following first result, that if your generator is a bounded operator, and if your system is hypocoercive, then the index can only be finite. Just two remarks on the proof in two stages. First, you show that the hypocoercivity condition, here I copied it again, is equivalent to this condition here. So the operator that you have here is, if you like, just half of the terms that appear in there. You take the image of this operator, you take the union of all these guys and look at the span. The question is this span your whole Hilbert space already? Secondly, and that's the key step, assume that this condition here holds only with m equal infinity, which would indicate that your index is infinite. If this is the case, then Bayes' category theorem would tell you that one of these sets here has to be non-meager, and then using the open mapping theorem, you will realize that this condition in fact already holds with a finite index. However, if your generator is an unbounded operator, then an infinite index can indeed appear. So again, let us look now at a bounded generator in a semi-dissipative setting. Then the next theorem that we found is that the generator is hypocoercive if and only if you have a finite integer index. So just by the wording, this results sound supernatural. But let's just interpret the left and right-hand side of that. The left-hand side, by definition, is a global statement on the exponential decay of your evolution. The right-hand side, if you like, is a local statement on the generator alone. So therefore, that's not a trivial relation. On the ODE level, this is rather easy to prove because you only have a finite spectrum, a finite number of eigenvalues. In the infinite dimensional case, it's not trivial. You have to work out that your spectrum stays away from the imaginary axis in a uniform way. And in fact, it is based on the following theorem, where this uniformity is somewhat encoded. So assume that you have a bounded generator, again in the semi-dissipative setting. Then we have the same short-time characterization that we already had in the ODE setting. So saying that the index m is also, or characterizes your dominant term here in this Taylor expansion, how you get away from the one in your propagator norm. With the small difference that in the ODE case we had a capital O here, in the infinite dimensional case I only have a small o, because in the infinite dimensional case we don't know if this propagator norm is analytic close to t equals 0 in the general case. So this is just a technical deficiency that we don't have here. So let me apply this previous result of this short-time behavior to this kinetic equation here, the Lorentz equation for a probability density in space and velocity, x being on the d-dimensional torus, and the velocities on the d-1 dimensional sphere. So it's well known, for example, due to work of Francois, that this operator, the transport operator, minus this collision operator generates a strongly continuous semigroup on this L2 space, and it's also known that the convergence to the steady state, which is a constant here, is exponential. So what I want to work out here is the question, what is the index here? So clearly this operator here is not bounded, so I slightly have to refine my definition. So I will only, so as a spoiler, the index will be 1, so I only take the first two terms of my hypocoercivity condition. Now I have to restrict it, or the set on which I consider that. Here in the definition, I have to apply twice the skew-symmetric part, which is the transport operator. So I have two spatial derivatives, therefore I have to require that the second x derivatives are also in L2. And I take out, say, the mass of the system, which is conserved anyhow, such that this is the system where this hypocoercivity condition should be satisfied. And the statement is, we've worked it out in detail in 2 dimensions, but in higher dimensions I'm sure it also works as well. The hypocoercivity condition here holds with a kappa that we can write down explicitly, and the index is equal to 1. So the way we proved that was to look at the Fourier decomposition in the x variable. Then the generators here for each spatial mode are bounded operators, and for those you check the hypocoercivity condition. And they are uniform in this index n. And when you check that, you work with infinite matrices which are due to the velocity moments on the circle. So to come towards the end of my talk, just let me give you a flavor of possible extensions that we could work on. And this extension, so now I think of time discrete systems in the sense of discretizing the continuous system with the spirit of having asymptotic preserving schemes, a scheme that preserves qualitative features of the original continuous equation. So let me take this ODE, or Hilbert space evolution equation, and let me just use the midpoint rule for that. So then here, this map would give you the step forward map with the operator A from time level k to k plus 1, and this map A is obtained from C via this combination that depends on the matrix C, where H is your discrete time step. So what you have here essentially is the Cayley transform from the matrix C to the matrix A. And the result that we have with Franz and Volker Mehrmann is the following. First, if the original matrix in your continuous system is hypocoercive, then your derived step forward matrix is hypocontractive, with which I mean that all eigenvalues of this matrix A in modulus are strictly smaller than 1. Second, the hypocoercivity index of the original matrix C is exactly the same as the hypocontractivity index of the step forward matrix A. And with this I mean that powers of this matrix A have a spectral norm exactly equal to 1. So this means up to the index m. So this means in your first m steps of stepping forward, your norm of the solution may not decay at all. Only when you go beyond the index, this norm will be smaller than 1. And this index is the same one as the C in the continuous equation. So what we see here, this delayed decay, might be a nice discrete analog of this Taylor expansion that I've shown you here for the continuous system. So let me conclude. I've shown you that the hypocoercivity index gives a nice characterization of the short-time behavior for ODEs, Fokker-Planck equations, or Hilbert space evolution equations. And we have two different regimes. First, the polynomial decay, and then the well-known exponential decay. And for non-symmetric Fokker-Planck equations, I was showing you that the fastest decay is connected to having a rather high hypocoercivity index. If we think of future continuations of this work, think, for example, of nonlinear evolution equations, I believe that a good definition of such a hypocoercivity index is probably strongly related to identifying the short-time behavior, that this is the key feature. Here are just some references. The link between hypocoercivity index and the characterization of the short-time behavior is in this joint work with Franz and Eric. The quest for the optimal non-symmetric Fokker-Planck equation in this paper with Bea Signorello, and the Hilbert space hypocoercivity in this joint work with Franz Volker Mehrmann and Edward Nigsch. So, thank you for your attention.
Thank you very much. Questions?
So, your definition of this hypocoercivity index, where you had the sum of these operators, is this somehow related to the commutator estimates that appear in the theory of hypocoercivity?
Yes. So the commutator relations, which are also envisioned in the book of Villani, for example, or related to the Hermann condition, this is both for the ODEs and for the Fokker-Planck equations, is an equivalent way of representing that, yes.
Let me perhaps go in that direction also. If you, at some point you introduced some, you looked at some kind of square root of the matrix that appears in your condition, right?
Yes.
Where you did the bare category argument, for instance, if I remember. So,
Yes.
Yeah, I mean,
sorry.
This, for instance.
Yes.
Yeah, so that vaguely looks like these Kalman conditions.
It's exactly that.
Oh, okay. So
yes.
Control in finite dimension.
Yes.
Right.
Yes.
So your condition here, it can be sort of wrapped up in terms of controllability of some system.
Yes.
Okay. All right. And so probably also with the observability, because these things are dual to each other.
Probably. So I know it more of what Volker Mehrmann, who comes from the control theory, explained me about the controllability. And there it is very closely linked to that.
Right.
In that community, they also, in parts of the literature, they speak about the controllability index, which is off by 1 from what we have defined here.
Yes. I was, well, it's not that I'm very much an expert of that, but since I've been a student of Claude Bardot's, I've been exposed to that very young. So, so I sort of got imprinted in my brain. So, other questions? Yes, sir?
Yes. So, concerning the second theorem you exposed about ODEs, so I was puzzled by the fact that there is no trajectory that achieved the optimal C.
Ah, yes.
And you said the way to reach this C is to consider the envelope of the solutions. Mm-hmm. And so how do you do that more explicitly? Because I would believe that the envelope is also a solution of some ODE itself, no?
It is the envelope of some ODEs, but the question would be, so let me go back to here. So, as I mentioned, the proof of that is split into an upper and a lower bound. And the difficult part is the sharp. So what is not so difficult is a lower bound of this form, but with a constant C that is not sharp. If you want the sharp constant, And if you just check, say, the different directions of your ODE, you would think, well, there's one worse direction. And if you take that one direction, it gives you the sharp C. And this doesn't work. So you must have a whole family of initial conditions. And it is, so the point is, it is not the evolution really at time equals 0 which determines it. But it's a whole family that a little bit after t equals 0 pushes up this constant and keeps it up such that the envelope stays above that. And therefore you need a whole family where you start not only at t equals 0, but you delay your start a little bit and take the envelope of that. And that will only determine the sharp constant C. And that for us was the technical difficulty to get here the sharp constant.
Oh, yeah. And I saw that you had this golden mean in the theorem of the very impressed with it. Yeah, I mean it's 3 minus square root of 5 divided by 2 for the. So that's the golden mean.
There I don't claim that this is the sharp constant.
Oh,
This.
I mean,
I didn't claim it. I didn't check. This was a reasonable way to establish the estimate. I cannot promise it's the sharp
Yeah.
one. Maybe it even is.
well,
I
because
didn't check.
the golden mean is the one which is the harder to approximate. It's the one that for which the rational approximation is the hardest, is the slowest to establish, right?
Yeah.
So perhaps since you're looking at some because you have some Fourier series on the torus,
Yes.
and probably some small divisors, it could still be the case, right?
Well, since you ask, I will check.
Yeah, I mean, maybe
Yeah.
that would be great if it was the case.
Okay, I'll try to find out.
Yeah, I would love to see that. Yes. Okay. All right. So, other questions?
Second, I can ask a small one. You had you didn't hide, but you said that the unbounded case for the theory is a lot more complicated. And when you discuss this, exactly the equation with the transport part, you went to a domain that was a very natural domain, and it worked. It was the second derivative is defined in H,
Oops,
right?
it's the wrong direction. Yeah.
And that you factored out the mass.
Yes.
Do you have any particular condition under which, a framework of condition under which you will investigate unbounded operator, or is it more a case-by-case study?
So far we only have a case-by-case study. So what is complete is the bounded generator case, and then for individual examples like this one and some Fokker-Planck equations, we have a case-by-case study. Not that the other one doesn't work, but we didn't attempt a more general theory for the unbounded operator case yet.
Mm-hmm.
It's on the list, but
Do you have any intuition to what you think to start with?
well, a little bit. So if you look back to the definition of the index, so a priori you don't know what is the maximal power j that could appear. So you will need to restrict your domain such that you can apply the skew-symmetric part really often. Well, unboundedly many times.
Mm-hmm.
So that a priori would require that you restrict your domain where you pose this condition very strongly.
Yeah.
Which is natural from the definition. So there, so the question is, since you have this sandwich structure, you start in your space, then you apply the skew-symmetric part many times possibly, then you have the symmetric part, and you still must be in the domain of the skew-symmetric part to some power. And so if the interplay between the symmetric and skew-symmetric part is very complicated, this might be difficult to handle. In this case, so with this Lorentz equation, this was fairly easy and explicit, so there we could manage.
Perhaps, since and these conditions should be understood as a positivity in terms of an operator, or
Yes.
could it be okay to have it in terms of a form, right? Yeah, so you see what I mean? So whether
Yeah, yeah, I
it's
know what
enough
you
to
mean.
think of a form domain of an operator?
Could be. Yeah, could be.
Because that's the second condition, right? It's
Yes.
CS.
Yeah. Could be. It could be, and it could be that this is easier for fixing the domain, because then you don't have to come back to the skew-symmetric part once
Exactly,
again.
exactly, yeah.
Yeah. But as I said, this is not done. There we are in an exploratory phase.
Yeah, sure. Sure, okay, so, I don't see anyone wishing to ask a questions. No more questions, so, okay. Thank you very much.